Okay, so we've been doing a whole bunch of point transformation and whatnot, and it makes sense that you would want to do this if you have multiple coordinate frames like camera coordinates and robot coordinates and whatnot. But let's talk about the specific example where you want to talk about how to do this for a robot manipulator, a robot arm. So, of course, we've had two different kinds of transformations that we've been talking about for a while now. We've had the T transformation from J to K, which is the transformation that is used all over the place. If I have a point that is already in J coordinates, but I want to know its location in K coordinates, I can pre-multiply it by this transformation. And of course, we found out that the easiest way to come up with the T matrix is to use this frame matrix to figure out how do I move frame K into alignment with frame J. And T from J to K is exactly the same as F from K to J. So if you imagine your standard robot manipulator, it has a bunch of things we call joints, right? The places where it bends. It has a bunch of things we call links, which are the solid pieces that connect the joints together. And it has a gripper, an end effector, something at the end that is its tool at the end, usually a gripper, sometimes something else. So there are two types of kinematic problems that people usually talk about with manipulators. One is if I know what the angles of each of these joints are, tell me what the big T transformation is from the base of the robot up to the gripper. So I change this joint. Now where is the gripper in world coordinates or robot base coordinates? And that is relatively straightforward, and we're going to talk about how to do that. You pretty much already know how to do it. The other problem is, I have some sort of a widget here. There's my widget. And I want my robot arm to reach over, assuming it could reach that widget. I can move it over, I think. Watch this. Oh, no, it moved the whole thing. Oh, well. All right. That was your entertainment for the day. Anyway, I want the robot arm to pick up this widget and imagine that the robot arm is a little bit bigger, and so it can pick up the widget. And I need to figure out what are the angles that I can move these joints to so that the gripper will be positioned perfectly to pick up the widget. And that's a little bit harder. That's called inverse kinematics, and we're not going to cover that this semester. So here's a very simple kind of an example. This is a 1 degree of freedom arm, right? The only movement that we have is in this one joint in the center. And if you look at this, there are 3 coordinate frames. There are world coordinates, which are whose origin is at the base of the manipulator. We have joint coordinates, which is centered on the middle of that joint, exactly where that thing rotates. And then we have gripper coordinates, which are located at some point relative to the center of the gripper. In this particular example, all of the x axes are currently aligned, all the y axes are currently aligned, all the z axes are currently aligned. And the important thing to notice here is I have this smiley, right? And the smiley's position in world coordinates is never going to change. But if I rotate this joint, all of a sudden, the location of the smiley in joint coordinates has changed, right? So joint coordinates used to have x pointing straight out this way, but now joint coordinates point x up that way. And so the location of the smiley in joint coordinates is going to have changed. The location of the smiley in gripper coordinates is also going to change. And that's even with a fixed gripper like we have here. If we could rotate the gripper, of course, that would change things even more. But even with a fixed gripper, x sub g now points up, right? The origin of the gripper coordinate frame is right here now. It used to be way down here. Well, here. So here's a question. You've seen the arm move sort of up and down, right? It rotates about this point again. And so what's the only point in this entire world, right? We know the smiley face wasn't a point. Smiley face was up here. That point changes location in W, J, and G coordinates. So what I want you to think about is, what is the only point in this whole system whose position doesn't change? Its XYZ position in world coordinates is always the same. Its XYZ position in joint coordinates is always the same. Its XYZ position in G coordinates is always the same. Even when the arm has moved like this, it's X, this mystery point we're looking for, it's XYZ in W, it's XYZ in J, and it's XYZ in G are all remain the same. And of course, the answer is it's this point right here, the origin of the joint coordinate frame, right? The origin of joint coordinates always, of course, stays in the same position relative to joint coordinates, right? It's always the origin. But because the very center of this joint, the joint rotates, the outside rotates, but the center point here, right where the middle of the smiley face is, always stays in the same position relative to world coordinates. And it also always stays in the same position relative to gripper coordinates, because of course the gripper coordinates, this is assuming of course this gripper doesn't rotate. The gripper coordinates always stay, relative to the very center of the joint, the gripper coordinates don't change. So our forward kinematic problem is, can I somehow figure out, can I just come up with a function? Can I for any given robot arm, can I come up with some function that lets me very rapidly compute both t from, say, world coordinates to gripper coordinates, and another function that lets me rapidly compute the t from gripper to world coordinates, right? I just want to be able to transform points between world and gripper coordinates in arbitrary order, and I want to be able to do the computation quickly. So I want to come up with some function that lets me do this. So let's start by just looking at, again, this very simple 1 degree of freedom robot arm. And let's suppose that it was fixed. The joint never rotated, right? And I wanted to figure out what is t from G to W, right? The transformation from the gripper coordinates to world coordinates, the homogeneous transformation that would take a point in gripper coordinates to a point in world coordinates. So, sorry, I'm busy trying to shrink this. So what would t from G to W? Well, we know we could figure that out, right? If nothing moves, then we have the same problem we've been doing all along. That is just, oops, that should say F. Woo, there's an F from W to G, right? And so all of the axes are in alignment, so it's really just a trans along the x direction, right? By how much? By L1 plus L2, right? So equals trans, let's see, can I make it a little bit smaller so I can fit this in here? Come on. Equals trans L1 plus L2, comma 0, comma 0, right? So that's easy. If the joint never rotates, then figuring out, this equation is pretty easy. But unfortunately, it does rotate, or fortunately, it does rotate, right? And it rotates about the z-axis, right, of the joint. And so if you think about it, we can do this as a two-step transformation, where this is sort of, or multi-step transformation, where this is an intermediate point, right? So what we can say is, well, let's first figure out the frame transformation from W to sort of unrotated joint coordinates, right? So we're going to figure out, maybe we will have an extra frame called frame 1, and we'll say, well, to get from W to unrotated joint chords, right? Let's call this step A. To get from world coordinates to unrotated joint coordinates, that's just this translate L1, 0, 0. Of course, then we have to do a rotation about the z-axis, right? So how much do we have to rotate? Well, I said, what if the joint is rotated by psi degrees? So what is that for our manipulator? Well, it's just a rotate z by psi degrees. So that's sort of B is from unrotated to rotated joint. So from unrotated joint coordinates to rotated joint coordinates. Not the most beautiful writing here, but you get the idea, right? From unrotated to rotated, I needed to take that rotate about z by phi. And so that is sort of step B. And then once I'm in j coordinates, right, I should have, suppose, instead of writing into rotated joint coordinates, I should have just written in the new j coordinates, right? That's what we have on this picture is j. And now I need to move from j coordinates up to gripper coordinates. How do I do that? Well, that's just a translate of this much along j's x-axis, right? So translate L2, 0, 0. So just to recap, I kind of did this in stages, right? The first thing I said was, how do I get from the base of my robot, maybe I do want it bigger, to the unrotated frame, right? That's just a trans, right? We're just going to do a whole bunch of trans and then rotates and then trans and rotates. That's just a trans. Then to align with the new rotated joint, I do a rotation about the z-axis in this case. Then to get to the next coordinate frame up, I do another translation. So we end up with this quantity. Okay, so I have already opened up and evaluated that notebook of mine that we've used before in Mathematica, where I have rot x, rot y, rot z, and the trans functions defined. I've also opened up the notebook and evaluated the one that had my point function. I'm going to do a new, open up a new notebook now. So what have we got? We've got our manipulators t from g to w equals trans of L1 comma 0 comma 0. What's L1? Well, it's just, it's L1. It's a variable. We can have that. It's some value. We can have that in Mathematica, no problem. Matrix multiplied by rot z of, there's a way to type in the Greek letter psi, but I'm just going to make it a variable. Matrix multiplied by trans of L2 comma 0 comma 0, and I evaluate that, and let's display it as a matrix, and we get this yucky thing, right? So let's just go back and take a look at the slides, and in the slides, I just call this manip TGW. I just use T from G to W. T from gripper to world coordinates. So that means that if we have a point in gripper coordinates, we can figure out its location in world coordinates. So let's just do a couple of tiny little sanity checks on that, right? So, you know, what happens if, for example, oops, sorry, come on, shrink a little bit. There we go. If we consider the point that is at the origin of gripper coordinates, right? So that is 0, 0, 0 in gripper coordinates. And if we say that this joint here is not rotated at all, then we figure that the location of that point, of course, assuming that this length is L1 and this length is L2, then the location of that point is just going to be a translation, sorry, the location of this point in this coordinate frame is going to be just L1 plus L2 in the x direction, right? So we can write that 0, 0, 0, sorry for the change of color, let's go back. 0, 0, 0 in ground, in gripper coordinates is the same as L1 plus L2, comma 0, 0 in world coordinates, right? Okay, so let's call my G origin is going to be, I'm going to use my point function, to make a point at 0, 0, 0. Right, that looks good. And if I say that, let's let psi equal 0. And so now I say, what is the location of my point in world coordinates? Well, I can just say what is the manip TGW. Well, now that's this quantity, right? Because I assigned what psi was. So we can matrix form this. And it's looking much nicer. And if I say, all right, let's take manip TGW and let's multiply it by G's origin and display as a matrix. And check it out. It is L1 plus L2, 0, 0, right? The point just like we eyeballed it. So that's a good sign. Or we could think for a minute, what would happen if the arm is rotated like that, right? And of course we need to come up with some convention for right, so here's the gripper, sorry. For what way is, how are we rotating? Since we decided it was a positive rotation about the z-axis and this way is positive, then I guess that direction is negative 90 degrees. So what we've got here is the point, let's see. So that's still in gripper coordinates. Let's do this in different color. That one. That is 0, 0, 0 in gripper coordinates. But if we think about, all right, there's our x, our y, and oopsie, our z for world coordinates. And so the question is, what is the location of this point here relative to world coordinates? And so we just have to say what's its x, y, and z. And it looks like its x is L1 units. And its y, which is the up down, right? So that's going to be negative L2 units. And the z, which is the in-out axis, right, is just going to be 0. So this is just, a sanity check. Let me try this. Now let me plug it into Mathematica and see if we actually get the right answer. And if we do, then we have a hope that maybe our answer is correct. Not guaranteed, but, there's hope. Okay, so we can say that, well, psi is now negative 90 degrees, which is negative pi over 2. So there's psi. And so now if we look at, if we take manip TGW and we multiply it by G origin and we evaluate that, and we put that into matrix form, display as a matrix. I mean, you can see already, but it looks pretty good. What did we get? L1, negative L2, 0. That's what we had before. So hooray, it sure seems like, if I change psi is now the value foo, and I say, what is my manip TGW function? Then display as a matrix. Then it looks like this has a good chance of actually being the equation for this manipulator over here, and all I need to do is find out what's the joint angle, and then I can figure out how to transform points from up here to down here, right? So how do I take a point that is in G coordinates and figure out, hey, what's its location in W coordinates? Let's just try one more example. I have reset psi to 0, so here is my homogeneous transformation matrix from G coordinates to world coordinates. And I just want to try one more experiment, which is what about the point that is 1 unit along X, the X axis in front of the gripper. So let me make a, I'm going to call it 1 unit equals my point 1, 0, 0. And of course, if I eyeball this, I figure in this coordinate frame, it should be L1 plus L2 plus 1, right? Should be the location along the x-axis in world coordinates, and the other 2 axes should be 0, but let's just try it. So I am going to say manip TGW matrix multiplied by 1 unit, and bingo. That looks pretty good. I could try it with a bunch more examples, but I don't want to make you watch them, so I'm going to stop here to go on to a slightly different problem. So let's look at a slightly different example on this same robot arm now. What I've done is, instead of saying that all of the coordinate frames for world coordinates and joint coordinates and gripper coordinates are all perfectly aligned when the robot is at its sort of 0 position, we can consider this the 0 position. What I've said is that the world coordinate frame and the joint coordinate frame are still sort of in alignment. You don't have to do any rotations to get between them. But check it out, gripper coordinates has X going up, Z going to the right, and Y coming out towards us out of the screen. I'm just using my right hand to make sure that X, Y, Z, yeah, so it's still a right-handed coordinate system. I didn't mess up here. So what you need to do again is you need to sort of do step by step. What you need to do is you need to say, all right, let's suppose that my joint is rotated about Z, and of course this is a positive rotation about Z, and it's possible that, you know, the arm is sort of down here, in which case it would be the value of this rotation, let's just call it theta. That theta value would be negative if the arm is pointing down, and positive if the arm is up here somewhere. But that's all fine. Essentially, what I want to know is what is the, I want to know what's the transformation. How do I take a point from gripper coordinates to world coordinates? And of course, in order to figure that out, I need to do the frame transformation from world coordinates to gripper coordinates. And so we're going to try and figure out, given an arbitrary rotation of theta about the z axis of this joint, what is the 4x4 homogeneous matrix that we can use to take a point from gripper coordinates to world coordinates, or to transform a frame from world coordinates into gripper coordinates. So that's what we're trying to figure out. And the big difference, we're trying to do exactly the same thing we did before, except the big difference now is that we do have to do some kind of rotation besides just allowing for this rotation here, because X, Y, and Z of my gripper don't align with X, Y, and Z of the world. So hang on while I clean this up for a minute. Okay, that's better. So what I want to do is I want to talk about, you basically, you need to imagine, you know, perhaps at any given time when you're trying to figure this out, your manipulator is in some fixed position, right? So I want to do this, and this angle is some sort of value theta, where I happen to know right now that that theta is going to be negative because my joint is pointing down, and I know the way the z points is out, so that's fine. But this is theta, right? So I don't care what value it has. I just know I'm going to have to do a rotate z of theta at some point. So, but what you want to imagine, if you were doing this this problem and I hadn't drawn a manipulator in here and you didn't know that this arm could rotate about here, you would just look at the individual coordinate frames that went along this manipulator, and you would figure out, wow, well, how do I deal with this? So what we're going to do is we're going to say, let's see, what are the frames that I need? What are the intermediate frames I need? And right now it looks like, just like before, that the first thing we need to do is we need to do a trans of a distance L1 along X, right? So we're using moving coordinates, right, to figure out, we're going to be figuring out F from W to G, because we know that actually equals T from G to W. And so the first move that I have is going to be translate L1 units along the x-axis. So that's just L1, 0, 0, just like before. Then we're going to do our rotation. I told you it was theta degrees. I don't have to say negative theta, because theta, just whatever theta is, it's got the value in it that is the number of degrees it's rotating. So trans L1, 0, 0 gets me into these sort of joint coordinates that you see on the screen. But just like with the previous one, we need to think about what happens after it's rotated. How do I rotate from this coordinate frame into the coordinate frame where the arm is pointing down like this, right? Which means that maybe now y is pointing sort of, that's diagonally up, not into the page, right? And x is pointing diagonally down, and z is still out of the page. So so what we need to do is we need to say, okay, after I do that trans L1, 0, 0, then to align with the next coordinate frame, I need to do a rotate about the z-axis of theta. Okay, so now my gripper is down here, right? And I'm going to try and draw the gripper coordinate frame accurately. So for the gripper, I'm not going to draw the y-axis. Y is pointing out of the screen of the gripper, but the gripper's z-axis is sort of pointing down and to the right, and the zipper's x-axis is pointing up like this, right, now that this has been twisted. So the next thing that I need to do, of course, is do this translate of along here, right? I've rotated. Now I need to translate this distance. What is that distance? Well, it's this distance, right? It's L2. So I'm going to do a translate of L2, 0, 0, right? And now I'm here, but my coordinate frames are wrong, right? My axes aren't pointing in the right direction, because I've done this this translate L1, 0, 0, and then rotate by about the z-axis of theta, and then translate L2, 0, 0. But when I get down here, my z-axis is still pointing out of the screen towards me, right? And y is sort of pointing up, and x is pointing out this way. But I don't want that. I don't want z pointing out towards me. I want y pointing out towards me. Why do I want y pointing out towards me? Because I got to get it into gripper coordinates, and gripper coordinates is defined this way for whatever reason. Gripper coordinates wanted to be defined this way. So we need to do one last, or maybe more than one last, I just made this up so I haven't tried it yet, set of rotations where we say, okay, let's get the coordinate frame, our sort of intermediate coordinate frame that's here, aligned with this one, right? And it's awfully hard for me to be doing all this drawing at an angle. So what I'm going to do is I'm just going to clean this up for a second. Hang on. All right, and what I'm going to say is, suppose at this point, if you look at the picture that I drew before, what I had was essentially I was at the gripper, but instead of this being z of gripper, in my coordinates, it's an x, right, pointing out. And in my coordinates, I have z, well, x is pointing to the right, z is pointing out of the screen towards me. So what I need to do is I need to align, essentially I need to figure out what's the rotation to take something that looks like this and rotate it into something that looks like this. So I'm just kind of looking at this. I'm starting here, and it sure looks to me like if I rotate the z around that way and the x around to the back to starters, that would be good. So because that would at least get my z lined up. So I'm going to do a rotation about y, and it's a positive rotation, right? So I'm going to do a rotate about y. Oops, sorry, rotate y. And now it's not a variable. Now it's just exactly 90 degrees, right? And then, and so now my z's are aligned, but I still have, let's see, the intermediate frame would have, I'm just going to draw it down here in the corner so you can kind of reference it. So now z is pointing to the right, and x is pointing back, and y, oops, that's an x, and y is pointing straight up. But I want my y to be facing forward, so out towards me. And so now I need to rotate about this z guy in a positive 90 degrees direction. So now I'm going to do rotate z by 90 degrees. Okay. The sort of moral of this story is not only do you need to move your frame to where it has to go with any variables of rotation about the joints, but once you kind of get there, you need to make sure that the axes are all in parallel. Well, are all lined up. Now, if you think about it, if we talk about a point that is at 0, 0, 0 in gripper coordinates, it doesn't really matter that I've changed the direction of x, y, and z in gripper coordinates. When I think about where is that point in world coordinates, the world coordinates frames are still the same, and the relative position of world coordinates and the point right here is still the same, or wherever it is, because it's always at the origin of gripper coordinates. So if I do those same computations, it should still work. So let me just show you what I mean. We'll call this the new G transform. Well, the new transform from, okay, how about the transform from new G to W, right? And what does that equal? Well, we said that is trans L1 comma 0 comma 0. Oops, there we go. Matrix multiplied by rot z of, well, this time we called it theta, that's fine. Matrix multiplied by trans of L2 comma 0 comma 0. Oops, I better read the capital. L2 comma 0 comma 0. Matrix multiplied by a rotation of y, about y of, oops, not 90 degrees, but pi over 2. And then matrix multiplied by a rotation about z of pi over 2. Boom. All right. And if we want to, we can display that as a matrix, and it looks equally hideous. And so what did I call it? G origin up here somewhere? Yeah, G origin. So let's see, what do we get if I say, hey, if theta equals 0, let's evaluate that. So I shift enter, and I want to take t new G to W and matrix multiply that by the G point at the origin, right? Because G origin was just 0, 0, 0. So, all right, it's the same as the new G origin. We get, let's display as a matrix. Oh, check it out. We say, all right, well, if my theta is 0, then this point in W coordinates is L1 plus L2 on the x-axis, 0, 0. So that looks good. And if we think about the situation where this arm was rotated down, right, the joint was rotated down by negative pi over 2, right, negative 90. So my theta would be, theta is actually negative pi over 2, and I shift enter. And so now I want to know what is my t new G to W, matrix multiplied by G origin, shift enter, and let's display that as a matrix. And now check it out, we have L1, negative L2, 0, 1. So the final example that we did with the original gripper coordinates was that we looked at a point that I called 1 unit, which, if I display as a matrix, was the point x is 1, y is 0, z is 0 in gripper coordinates. So now that we have these rotated ones, that's probably located about here, right? So the question is, if I take, let's make sure that theta is 0, and let's see if I say, where is this point relative to world coordinates? We would expect it would be L1 plus L2 along the x-axis, and then relative to world coordinates, we have to go up 1 along the y-axis and 0 on the z. So let's see if that's what we get. So if we say, what is T nu G to W matrix multiplied by my 1 unit, shift enter, and we display as a matrix, presto, change-o, nothing up my sleeve, but you have to go L1 plus L2 along the x-axis and then 1 up along the y-axis. That's W's y-axis, right? Because we're taking a point in gripper coordinates, which was the point 1, 0, 0 right here, and we're saying, where is that located relative to the world coordinate frame? Amazing. Again, no guarantee that it's perfect, no guarantee that my nu G to W, T nu G to W matrix is correct, but I'm feeling better about it. And of course, another way that we could do this whole problem is, instead of starting with all the movement, we could start with the rotation. So let's just try that and see how that would work. So what we could do is, is we could say, all right, well, what I'm going to do from the start, can I put that up there? Is I'm going to say, all right, well, I started with y pointing up, x pointing to the right, and z pointing out towards me. And the first thing I'm going to do is try to do the rotations that align it with this other guy. So I'm going to do, well, actually, I know what those rotations are. First, I rotate about y by 90 and then rotate about z by 90. So I'm going to do a rotate y by 90 and a rotate z by 90. But now I need to be careful, because this forward movement along the link is no longer in the x direction. Now it is in, what direction is that? The z direction, right? Because I turned this green guy into a situation where that direction is actually z for my gripper, right? But it's z for my intermediate point, right? Because here I'm at my intermediate point after just doing these two things. So z for my intermediate point points to the right, and y for my intermediate point points out of the screen, and x for my intermediate point points up. So now when I want to do this this translation along L1, it's going to be translation along z, right? So instead of saying trans L1 0 0, I am now going to write translate, what did I say? It's going along the z, so 0 0 L1. And for the rotation, I've already said that now I'm going to be doing a rotation about the y-axis, right? Because now it's the y-axis that's pointing out. So instead of rotating about z by theta, I'm going to rotate about y by theta. Then I'm going to do a translation along this second link, right? So that means that I'm going L2, a length of L2, but that length of L2 has to, again, be along, I've called my axis Z, so I'm going to have to do trans 0 0 L2, and oh, hey, check it out. Now I've arrived at this point, right? My origin's co-located. The origin of my intermediate thing is now co-located with the origin of my gripper coordinate frame. And furthermore, my axes are aligned, right? X points up for my sort of where I am now, and X points up for the gripper, and Z points to the right, and Z points to the right. So I'm done. And so the magic here, of course, is that if I compute what this thing is, it should have the same exact value as this thing. So why don't we say that theta is going to have the value of, I don't know, epsilon. I just got to give it some sort of a value so that I can look at my T nu G to W. That was the previous one, right? And I can display that as a matrix. So this is our original matrix that we got from doing these multiplications. And my hypothesis is I do these multiplications, I should get exactly the same thing, right? So let's see. Let's say hoping same matrix is going to be, let's see, rot y by pi over 2, matrix multiplied by rot z of pi over 2, matrix multiplied by trans of 0, 0, L1, matrix multiplied by rot y of theta, which we're calling epsilon, matrix multiplied by, oh, well, we could call it theta, couldn't we? Rot y of theta, because that's the same thing. Matrix multiplied by trans of 0, 0, L2. And let's see, if I say display this as a matrix, whoo, it sure looks the same to me. And let's just say T nu G to W equals. Let's try that. Hoping same matrix, and we get true. Amazing. So even though we did a bunch of different matrix multiplications, we still got the same thing. Okay, last example. I just want to show you an example with two joints. So, and again, I've decided to make the example more complicated by saying that the world coordinates and gripper coordinates are not aligned, right? If their origins were co-located, X, Y, and Z would be pointing in different directions. And so what I'm going to do real quick is just sort of step you through all of the intermediate frames that I need to think about in order to solve this problem. There's a lot of them. So up here is the original coordinate frame we've been talking, or the original manipulator that we've been talking about. And what I've done just to make it a little bit more obvious is I've said, okay, well, I want to show you what things look like with the arm sort of rotated different places. All right, with the two joints rotated. So let's suppose that this first joint is rotated at an angle of theta 1, and the second joint is rotated at an angle of theta 2. Okay, well, the first sort of step in moving along to figure out what are all the different intermediate frames that we have is just moving along L1, right? And so that puts us into a coordinate frame. I call this frame J1. Where the axes are sort of in alignment with my original one, but it's been moved over to the center of the joint, right? And this point right here doesn't exactly look like I've drawn it perfectly, but it should be centered right on the center of rotation there, okay? So that's sort of the before we even did this rotation. I wish in some sense I could kind of cover up with my hand this bit, right? So that's our first intermediate location, and this doesn't really line up with the picture yet because with the picture it's sort of rotated. So this light blue axis I've called J1 prime because it's sort of the joint after it's been rotated, right? And so now Z for J1 prime isn't pointing straight up anymore. It's sort of kind of up and to the right a little bit. Y is drawn horribly but is still pointing into the board. And X is now going along that link too. So J1 prime is another intermediate coordinate frame that we need. Here's the next coordinate frame that we need, the next intermediate one, which is sort of what happens when we do the translation down to here. So J2 is, the axis for J2 is in alignment with the axis for J1 prime, right? And then we've got another set of axes, these J2 prime, that I guess which axis, oh, this is so hideous and hard. I guess Y is pointing into the screen, right? So this is some sort of a rotation about Y, and I guess in this case it's a negative rotation, just because Y is pointing in, and when I align my thumb with it, a positive rotation would be in this direction, but we went this direction for joint 2. So theta 2 is going to have a negative value. Not that it really makes that much of a difference to us. We just call it theta 2. Okay, and we're going to need to move, obviously, our origin. We're going to need to do some sort of a translate up to here. And so I've made another coordinate frame called GG. And GG is what we're going to do after we're in this J2 prime intermediate phase. So we'll do a translate. I guess we're translating, in this case, it's going to be along the X direction, right? And then after we get here, we still need to do some final rotations to get us so that we are in alignment with the G coordinate frame. It looks like in this particular example, it's just going to be a single rotation about GG's x-axis because that's already aligned up with x sub g. So let's just do the whole thing looking at all these different axes. And I'll just see if I can write all of the steps on the right-hand side here, just from start to finish. So the first thing we need to do is we're going to do a translate, and it looks like it's along the x-axis by L1, 0, 0. Then that gets us to J1, right? So we could sort of write intermediate states here. So we started at world coordinates, and now we're at J1 coordinates, and then I'm going to have to multiply that. I'm going to have to rotate about the y-axis, whatever theta is. So I'm going to, theta 1, I'm sorry, so I'm going to do a rotate y of theta 1. And so now I'm sort of at the J1 prime axis. And so now I need to do another translate, in this case, along the x again to get me over there. And I'm going to be translating by however long L2 is. So I'm going to do a translate of L2, 0, 0. And so now I'm, I guess, in J2 coordinates. But now I need to rotate about y again so I can get to J2 prime. So I'm going to do a rotation about y of whatever the value of theta 2 is. And that puts me in J2 prime coordinates. And now I'm going to do a translate along x again, L3, 0, 0. And then finally, so that puts me in GG coordinates, right? These little notes along the edge here are just for me to keep track. What coordinate frame am I in now? What coordinate frame I am now? And so the very last thing that I need to do is I need to do a rotation. It looks like 180. So I need to do a rotation about the x-axis. Oops, rod x by 180 degrees. And it looks like that should get me so that I'm at my GG axis. So if I multiplied all these together left to right, I would get the transformation between, well, I would get F from world to G, which equals T from gripper to world. So let's just try one more example. I'm going to say that this is the natural sort of zeroed out position of this particular manipulator. It's a ridiculous zero position, but it will just help us do a crazy example. And let's suppose that that this length is L1, this length is L2, this length is L3. And our rotations are going to be a rotation of theta 1 and theta 2. And we'll say that our rotations are both clockwise. So we're going to go theta 1 degrees clockwise, and we'll figure out what that means in a minute, and theta 2 degrees clockwise. And of course, just as an aside, if theta 1 is a negative value, then it will in fact be going counterclockwise, but yeah, that's all fine. So let me just see if I can squidge, yes, squidge all this up, and let's just write out what we have to do. So this is how we're starting. And so, for example, if we wanted to just straighten this whole thing out, then theta 1 would be, since it's clockwise and that's clockwise, theta 1 would be a 90-degree rotation, and theta 2 would be a negative 90-degree rotation, right? So we had everything lined up. But let's just say this is my 0, 0 position, and I want to do a rotation of theta 1, a rotation of theta 2. So what do we got here? Well, we're going to start, of course, by translating, and again, it looks like L1 is along my X, so, oops, I'm in red. I guess we'll stick with that. Translate L1, 0, 0, and then we will do a clockwise rotation. Now, Y is pointing into the sheet, into the paper, so, or into the screen, so that means that clockwise is in fact positive. That's nice. So now we will do a rotate about Y of theta 1. And so at this point, after we've done that, we need to go in this direction by a length of L2. What's this direction? Well, my intermediate frame that I've got over here has X pointing to the right and Y pointing into the picture and Z pointing up, just like my original frame did. So I guess now I have to do a trans of 0, 0, L2 because Z points up, right? And of course, even if the rotation that I did about the y-axis, Z would point along the length of this joint. Sorry, along the length of this link. Right. So now we're here, and we need to do a rotation again clockwise. So, and again, we're still rotating about Y because now Y is our intermediate frame has Y centered here and pointing into the page. So we will do a rotate Y of theta 2. And finally, we need to move over to co-locate our intermediate frame with the gripper coordinates. So that will be another trans, this time in the X direction. So L3, 0, 0. And now let's see, we've got our axes are totally out of whack. So we need to do some set of rotations so that they will line up. So I'm going to start by trying to line up the Z axis, right? So what I want to try and do is right now my intermediate frame has that direction is X and up is Z, right? And Y is pointing in. And so what I'm going to do, the first move that I'm going to do is I'm going to try and take the Z, rotate it down like that. So I'll be doing a rotation about the X axis of positive 90. So I'll do a rot X 90. And so now my Z's will line up. My Y is pointing straight up, and my X is still that way, and that's my Y. But I actually want my Y to be down here, so it lines up with gripper coordinates. So I need to rotate my Z, and I'm going to do that negative 90. So I'm going to do a, oops, different color, rotate Z, negative 90. And if I multiply all these guys together, I should be there. I should have the right answer. So let's say that the T transformation from, the T transformation on example, I don't know, are we on example 3, example 4? Let's call it example 4. I think it might be example 4. From G to W is equal to trans L1, L1 comma 0 comma 0, matrix multiplied by y of theta 1, matrix multiplied by a trans of 0 comma 0 comma L2, matrix multiplied by y of theta 2, matrix multiplied by trans of L3 comma 0 comma 0, matrix multiplied by rot x of 90, which is pi over 2, matrix multiplied by a rot z of negative pi over 2. Boom. Boy, oh boy, is that the most hideous thing you've ever seen if we at least look at it in matrix form. And in fact, this is so hideous you can't actually see the whole thing in matrix form on the screen, but it's really there. So we'll use this in a minute. Okay, so let's just come up with a couple of sanity check positions for this manipulator. I just want to say, let me just throw in a couple of points and see whether the points do in fact convert nicely. So one easy thing to check is what happens if, let's see, so in this case, in this configuration, oops, wow, I didn't expect that to happen. In this configuration, I've got theta 1 clockwise was positive, right? So theta 1 is going to be 90 degrees. And here theta 2 is actually negative 90, right, to get this position. And what I want to see is what's the location of this point in world coordinates. That point is actually the point 0, 0, 0 in gripper coordinates, right? So we'll try and transfer that into world coordinates and see what happens. So what do we expect to happen if I take 0, 0, 0 in gripper coordinates and turn it into world coordinates when I have these rotations? Well, I expect excuse me, that the location in world coordinates is just going to be L1 plus L2 plus L3, right? So let's try it. If I take, I think I already have, yep, I have a point called origin. So if I take TEX for, oh no, wait, I got to tell it the rotation. So theta 1 is equal to pi over 2, and theta 2 is equal to negative pi over 2. And now I'm going to do text. Oops, text. No, I didn't want text words, sorry. Text for G to W, matrix multiplied by the point origin. And look at that. Display as matrix. Ta-dum! Impressed? I'm impressed. Darn. I don't understand why the two things are moving separately, but we'll ignore that for a minute. And then maybe we'll just make one more sanity check where, let's see, suppose that our robot looked like that, and then the arm goes up, and then actually, the arm keeps going up. So here's my gripper, right? So in that case, suppose again, I want to look at the point here at the origin and say, where is that relative to, you know, if I'm looking at it in world coordinates. And so in this case, theta 1 would be 0, right? Because I didn't change theta 1, but theta 2 is still negative 90 degrees. So the blue one was L1 plus L2 plus L3 comma 0, 0 in world coordinates, right? And on the green one, 0, 0, 0 in gripper coordinates, right? This origin point up here is going to be, I'm going to have to do L1 in that direction, L2 plus L3 in that direction. So this direction is X, so it's going to be L1. And then up direction is Z, so it's going to be L2 plus L3. Oh, Z, so we'll put a 0 in there. Sorry. So L1, comma 0, comma L2 plus L3. That's sort of what we expect 0, 0, 0 in gripper coordinates to be. So let's try it. Let's say that theta 1 is now actually 0. And theta 2 is now negative pi over 2. And so we take our same origin point and we multiply it by, what did we call it? T. Example 4, blah, blah. Matrix multiplied by origin. And like magic, displays a matrix. Look at that, L1, 0, L2 plus L3, L1, 0, L2 plus L3. We are amazing.